In the previous class, we have derived the Lagrangian density function for charged scalar particle, and the result was this. And actually, the overall normalization has not been determined clearly, but in order to satisfy the equation of motion, we are free to multiply over a factor to the Lagrangian density function. There are many choices of choosing the Lagrangian density function's normalization, but in this class, let us modify the overall normalization to have better understanding of probability density. Suppose if we integrate over the space, the Lagrangian density function becomes Lagrangian, and it has the dimension of energy. Because the Lagrangian is kinetic energy subtracted by potential energy, it has the dimension of energy. In the previous derivation, we have a rather complicated dimension. But why don't we pull out mc squared, that is the dimension of energy, and if we integrate over the space, if psi star psi is interpreted to be the number density of the particle. So if we integrate over the space, if we consider a single particle, then the integral over the phi star phi must be 1, something like that. Then it is better to understand, so why don't we pull this over factor out, m, single power of m and h bar squared. So in that case, our final result for the Lagrangian density function is modified to be h bar squared over m, round mu phi star and the round mu subtracted by mc squared psi star phi star phi. If we consider the electromagnetic interaction, the Hamiltonian is replaced by Hamiltonian subtracted by electrostatic potential, and momentum was replaced with conjugate momentum subtracted by q over c vector potential. This whole thing can be interpreted in a covariant way in a very simple form. Normal derivative, covariant derivative replaced by the gauge covariant derivative, that is sum of covariant derivative plus iq over h bar c for vector potential. So we would like to substitute this covariant derivative into this expression. First, we replace this covariant derivative with gauge covariant derivative, and then final result is like that. If we look into this expression, we have new expression, new contribution compared with the free particle case, in which only the covariant derivative appear. In this case, we have a linear term in a mu, and we have a squared term, a mu, a squared term. And if we consider the fact that this charge is small, in that case, we can make a perturbation theory to consider the a mu contribution order by order. Anyway, this expression has no gauge dependence. On the other expression, that if we make a gauge transformation from the vector potential, full vector potential a mu is transformed into a prime mu by adding derivative of a scalar function, then the wave function for the charged scalar field is transformed by multiplying the unitary matrix U. And this Lagrangian is invariant under this gauge transformation only if this guy satisfies this kind of relation. Do we have additional factor in front of this? h bar c should be in here. Okay. Let us recall the shape of transformation. if we apply the gauge transformation, covariant derivative changes because A mu is replaced with A prime mu that has additional contribution, and phi is transformed into U phi, and this additional piece is cancelled, so that this U used to be here, but that U passes the covariant new covariant derivative, come back to the original covariant derivative. So that if we square these expressions, our final result is the same as original result. Okay? The same is true for the mass term, mc squared. This mass term is invariant under gauge transformation. And we already noticed that there is additional contribution coming from the gauge field, that is photons' four-vector potential. But we recall this Lagrangian satisfies Maxwell's equation with some current, external current. So what I'd like to do is, the first one is the kinetic term for the photon, and this term is the kinetic term for the charged particle. But as soon as I introduce the gauge covariant derivative, suddenly there is an interaction between the photon and the charged particle emerges. That can be identified to be the source term for the Maxwell's equation. So this current can be identified from this expression directly. Okay? Let us expand this one, removing the A squared term and just consider the linear term in A mu. Then that can be done by here, the covariant derivative of phi, complex conjugate has this term. Without that, this. So the term linear in A mu is just this guy multiplied by this and this guy multiplied by this. If we collect only that term, there are two terms. Over factor is minus IQ over H bar C. Remember we have over factor H bar square over M multiplied. So if we multiply H bar square over M, then this H bar in the denominator move into the numerator, and M appears in the denominator. So H bar M, and still there is a C in the denominator. Okay, and A mu is here. All right, and what's that? Phi star and derivative here. If we consider this term, this contribution is a plus IQ H bar over MC, and the other part is around mu phi star multiplied by A mu. Okay, so I'd like to find this expression. So if we pull the A mu out and pull the 1 over C in front, keeping the negative sign in front of it, the final expression looks like that. IQ H bar over M, C is pulled out, and phi star around mu phi, and the same thing except that I have negative sign, and derivative is applied to the complex conjugate. Right? So if we pull this Q over M out, what we find is phi star round mu phi minus round mu phi star phi. But let us recall the fact that IH bar round mu, covariant derivative is multiplied by IH bar. Then what I have is IH bar 1 over C time derivative and minus IH bar spatial derivative. And we know that this is a 3 momentum operator, and this is the energy operator, actually Hamiltonian operator divided by speed of light. The head represent this is operator, derivative operator with respect to time and space. So if we replace this partial mu multiplied by IH bar, then I can simplify the whole expression for the current, electromagnetic current generated by the charged particle's motion is charge divided by mass multiplied by momentum. Actually, for momentum. Okay? And crudely speaking, roughly speaking, this is for momentum divided by mass, rest mass. So for momentum divided by rest mass is actually for velocity. So this current can be interpreted to be charge times the full velocity of the particle, and it is proportional to the number density phi star phi probability density times velocity times charge. Interesting thing here is that if we have real field, if phi star is equal to phi, this is always 0. So if we make use of this result, we can find that neutral particle can be expressed in terms of real scalar field, but if we want to consider the charged particle that interacts with the electromagnetic field, then we have to introduce the complex scalar field. That's it.